Alright, in this video, we will review some sets of numbers that you already know, you should be familiar with already, and also study some of the most important properties of real numbers. Okay, let's start. The first set of numbers we study is the set of natural numbers. Of course, you know what natural numbers are, and we denote the set of natural numbers by this n, and this is the set of numbers such as 1, 2, 3, 4, 5, and so on. And I assume that you know what this means, okay? So it's just natural numbers. It's the numbers that appears in counting things, like just 1, 2, 3, and so on. And sometimes it's convenient to include 0 as a member of the set of natural numbers. In that case, in this lecture, we write like this, n0, which includes 0, 1, 2, 3, and so on. So if you know some set operations, which we will introduce more formally in the next lecture, this may be written as the union of the set of 0 and the set of natural numbers. Okay. And what's important to note about natural numbers is that they are linearly ordered. That means 1 is less than 2, which is less than 3, which is less than 4, and so on. So it is naturally linearly ordered. So there is an order in this set. So we summarize this fact as the following axiom, which is called the principle of well-ordering. Principle of well-ordering. Well-ordering in the set of natural numbers. That is, every subset of the set of natural numbers has a least integer. Least integer, it's an actual natural number. Number in it. Let's call this subset as S in. So if S is a subset of the set of natural numbers, then there is a least natural number in that set, S. Okay, so of course, the set of natural number itself is a subset of the set of natural numbers. In that case, the least element is 1, naturally. Sometimes we want to prove a theorem or statement that depend on a natural number. In other words, we want to prove that a predicate that depends on a natural number n is true. Okay. For example, you may know this formula, 1 plus 2 plus 3 plus and so on. So the sum of natural numbers from 1 to n is equal to n times n plus 1 divided by 2. Okay, so this entire equation may be considered as a predicate that depends on this n, natural number. Okay, so let's see if this formula is true. When n is equal to 1, then the left-hand side is equal to 1, and the right-hand side is equal to 1 times 1 plus 1 divided by 2, which is equal to 1. So this formula is true. So P of 1 is true. Okay, when n is equal to 2, Then left hand side is 1 plus 2, which is 3. And the right hand side is 2 times 2 plus 1 divided by 2 is 3. So therefore the right hand side is equal to the left hand side, so P of 2 is true. And we can continue this forever, but actually we cannot do it. So how do we actually prove that this formula is true for all natural numbers n? So that is the next question. And to prove this, we use a technique called mathematical induction, which we introduce as an axiom. So mathematical induction, called induction, or simply induction. In a philosophical sense, this is not really an induction. So induction means you conclude something from various examples, okay? But this is not the case here. Mathematical induction is actually deduction. Anyway, this principle of mathematical induction can be derived from the principle of well-ordering of natural numbers, but here we introduce it as an axiom. So here it goes. First, we prove P of 1 is true. Okay, when n is equal to 1, a predicate is true. Okay, then second step, prove that if P of k is true, okay, assuming P of k is some integer, some natural number, then P of k plus 1 is true. Okay, if these two steps are satisfied, then we conclude that P of n is true for all natural numbers. Okay, so prove this, and we can prove that. Okay, that is the way we can prove a predicate or statement that depends on arbitrary natural numbers. Okay, so let's show how we can prove that this formula of summation using mathematical induction. Okay, so first thing we need to do is, so let's prove this. Let's prove this. Plus 1 divided by 2. Okay, first we prove that when n is equal to 1, the left-hand side is equal to 1, obviously, and the right-hand side is equal to 1 times 1 plus 1 divided by 2, which is equal to 1. So the left-hand side is equal to the right-hand side. Therefore, the formula is, let's say, the formula is true. And second step, suppose, so here's this assumption part, suppose the formula is true for n equal to k. Then we have this 1 plus 2 plus and so on up to k is equal to k times k plus 1 is equal to divided by 2. Okay, so this we can use this as given, okay, because we're just assuming it. Okay, then when n is equal to k plus 1, then the left-hand side is equal to 1 plus 2 plus 3 plus and so on, k plus and k plus 1. Okay. However, this part is equal to this, right? So because by assumption it is equal to k times k plus 1 divided by 2. Okay, plus we have extra k plus 1 here. Okay, now we have a common factor k plus 1 and k plus 1 here. So let's factorize. So k plus 1 and k over 2 plus 1, right? So that is k plus 1 and common denominator k plus 2 divide by 2. Okay, so we have k plus 1 and k plus 2 is k plus 1 plus 1, right? Divide by 2. And so the left-hand side is equal to this. The right-hand side is, of course, if we replace n with k plus 1 in the formula, what we get is k plus 1 and times k plus 1 plus 1 divided by 2, which is equal to the left-hand side. Therefore, by step 1 and step 2, the formula is true. True for all natural numbers. And we are done. Okay, enough about natural numbers so far. And next set of numbers is the set of integers, which we usually denote by this symbol, z. Okay, so this is a set of negative integers and positive integers, right? Of course, we are defining integers here. I assume that you already know what integers are, okay? And so it's just positive part and negative part and 0, okay? So negative of natural numbers, okay? And we can add and multiply, subtract, and as integers, okay? Division may be problematic, but we can define division between integers by including remainders, okay? Okay. By the way, we use z for integers. This symbol comes from a German word called Zahl, which means number in German. Zahl. Okay. Okay. Next, rational numbers. And which we use the symbol Q. Okay, Q comes from quotient because rational numbers are the numbers that can be expressed as the ratio between integers. Okay, and m over n. I assume what you know that what this means. Okay, and m and n are integers, and n cannot be 0. Okay, the denominator is non-zero. So all numbers that can be expressed as the ratio between two integers is rational numbers. But if you think about it, what this notation means is not actually trivial, but it requires some deep consideration. But we just assume that we already know what this means, okay? And you can add, multiply, subtract, and divide rational numbers. The division is defined for non-zero rational numbers. If you want to divide by some rational number, that rational number cannot be 0. Okay. And the next is the set of real numbers. Okay, which we denote by R. And real numbers, the set of real numbers is the set of numbers that are rational numbers and irrational numbers. And what is an irrational number? It's an number that cannot be expressed in terms of a ratio between integers. Okay, for example, square root of 2, that is 1.4 hitoyo hitoyo ni hitomi goro. So it's in Japanese there's a way of remembering this. So this continues forever and no patterns of digits will repeat. Okay. So the square root of 2 is an irrational number. So the set of both rational and irrational numbers is called real numbers. Actually, defining real numbers is not a trivial business, and it's really, really hard. So we don't talk about it, but if you're interested, maybe you can study it in some advanced course. Okay, so to begin with, let's prove that square root of 2 is actually irrational. Okay, so how do we prove that? So this is a lemma. Square root of 2 is irrational. So how do we prove this? Okay, in order to prove something, we first have to understand what we want to prove. Okay, here we want to prove that square root of 2 is irrational. But what does irrational mean? It means not rational, right? Obviously. So it's actually a negative statement. So in general, as a general strategy of proving something, if what we want to prove is some negative statement, it is often useful to use the method of proof by contradiction. Okay, so let's use that. So here's the proof. So in order to prove by contradiction, we first assume that the negative of this. So suppose square root of 2 is a rational number. Okay, then square root of 2 can be expressed as m over n, where m and n are integers and n is not equal to 0. So what this implies is this. Okay, further assume that we may assume that m and n have no common factor. Okay, so that means this expression is already reduced form. Okay, so no common divisor. So by multiplying both sides by n, we have square root of 2 times n is equal to m. Okay, and by squaring both sides, we have 2n squared is equal to m squared. Okay, so this means m squared is a multiple of 2. Okay, so this implies that m is also a multiple of 2. So this may not be trivial to you, but you should check what if this is not the case. So multiple of 2 means that m is even, okay? So if m is not even, m squared, it cannot be an even number, okay? So that is a contradiction again. So if m squared is an even number, then m itself must be an even number. So therefore, m is expressed as 2 times k, where k is some integer. Okay. Now, if we substitute this m, k, 2k into this, then we have 2n squared is equal to 2k squared, that is 4k squared. Therefore, we have n squared is equal to 2k squared. So that means n squared is an even number. By the same argument, therefore, n is an even number. So n can be expressed as a multiple of 2, where l is an integer. But by assumption, m and n had no common factor. But here we are. M is an even number and n is an even number. So they have the common factor 2, which is a contradiction. This is a contradiction. Therefore, square root of 2 is irrational, not rational. Because this contradiction was derived from the assumption that this is a not rational number. So this must be wrong. Okay, this must be false. So we are done with the proof that square root of 2 is a rational number. Okay, so now we know that the set of rational numbers is a subset. It's a proper subset of the set of real numbers. And there is a huge difference between these two sets, but we are not going to discuss in detail what really the real numbers are. But instead, we introduce one axiom called the principle of Archimedes principle, or Archimedean property. Okay, here's an axiom. Archimedes principle. Okay, that is for any real numbers, a, b in real numbers, and if a is positive, then there exists some natural number such that a n is greater than b. So for any real numbers, we have this, a and b. However small a is, as long as it's positive, we can make it bigger than b by multiplying by some natural number n. So if n is big enough, then however large b is, or however small a is, as long as it's positive, we can have this inequality. So this is one of the properties that characterizes the set of real numbers. Okay, we take this as an axiom of real numbers. Actually, this axiom is a theorem that can be derived from other basic properties of real numbers, but that will be explained in a later video. But for now, we just accept this as an axiom. Okay, now let's use this axiom to prove the denseness of the set of rational numbers and the set of real numbers. Okay, denseness. So these sets are dense in the sense that if there are two numbers, let's say whether it's rational or real, it doesn't matter. So if a is less than b, then we can always have some number between a and b. Okay. So there exists some rational number such that a is less than x, which is less than b. And also, we have some irrational number. We don't have any specific symbol for the set of irrational numbers, so just write like this. Y being irrational, such that a is less than y which is less than b. So for the sake of convenience, let's just say a and b are any real numbers. Okay, so we have this property. So in this sense, if there are two different real numbers, we can always find some rational or irrational numbers between these two numbers. So that's called denseness of these sets. Okay, so let's prove this theorem. Okay, so let's prove this. First of all, by Archimedes' principle. There exists some natural number n such that 1 over n is less than b minus a. Okay, so how did we apply Archimedes' principle here? First of all, b minus a is positive, and 1 is a real number, of course. So there exists some natural number such that b minus a times n is greater than 1. By dividing both sides by n, we have this. Okay. So that's the first step. And next step, let z be an integer such that b times n is greater than z, and also be the minimal, the least integer such that this holds. Okay, what this means is this. So b is a real number and n is a natural number. So this times this is so b times n is a real number. So we can always find some integers that are greater than this number, right? So among those integers, we pick the least integer, and that is named z here. Okay. So that's how we choose this integer z. So by this choice, we have z minus 1 is less than bn, because z was the least integer that is greater than b times n. Okay, so we have this inequality. So divide everything by n, we have z minus 1 over n less than b less than equal z over n. Okay, now let's use this inequality to prove this. A is first is equal to b minus a. Okay, so we just added b and subtracted b and just reorganized the equation. So a is just equal to this. And here we have b minus a, which appeared here. Okay, so b minus a is greater than 1 over n. So we have negative sign here. So this is greater than, less than b minus 1 minus n. Okay, so this one. Okay, so and now we have this b here, and that is, let's see, b is less than or equal to z over n. So less than equal to z over n. So we have this, and this is equal to z minus 1 over n. But z minus 1 over n is here. That is less than b. So this is less than b. So that is a is less than this number, and which is less than b. Okay? But by the way we chose z, this is an integer. So integer minus integer is an integer. Integer divided by integer is a rational number. So let's define x as z minus 1 over n. So this is definition. Then this is a rational number, which is greater than a and less than b. So a less than x less than b. So that's the rational number we were looking for. So between any real numbers a and b, we can find the rational number x like this. Next, we try to find an irrational number between a and b. And for that, again, we apply Archimedes' principle, so that so there exists some natural number m, such that let's say b minus x times m is greater than square root of 2. Okay, so this x is this x. So this x, this x. Okay. So b minus x is a positive number because b is greater than x. Okay. So any positive number, any real number, in this case it's square root of 2, we can always find a natural number m such that this inequality holds according to Archimedes' principle. Okay, now let's define y as x plus square root of 2 divided by m. So this m is this m. Okay. Now, how does this y evaluate? So by this definition, by the way, this is not rational number. Okay. Because x is rational and m is a natural number, so if y is a rational number, then that means, so if we move x to, if we subtract x from both sides and multiply by m both sides, we have square root of 2 equals to m times y minus x. So if y is a rational number, then rational number minus rational number is a rational number, and rational number multiplied by a natural number is a rational number. So this would be a rational number. But square root of 2 is not a rational number, so that is a contradiction. Therefore, this is irrational. Okay, y is an irrational number. Now, so square root of 2 is positive, natural number m is positive, so x is less than y. Okay, and y is x plus square root of 2 over m. And square root of 2 is, wait a minute, square root of 2 is less than this number. So that is x plus b minus x m. So this is less than this and divided by m. So m is cancelled. We have x plus b minus x, which, so x and x, this cancel. We have b. So x is less than y and y is less than b. By the way, x was greater than a. So therefore, a is less than y and y is less than b, and y is between a and b, and y is irrational. So we found that number, and that's it. Proof is done. All right, finally we introduce the set of complex numbers. We denote the set of complex numbers by C. Of course, this C represents complex numbers. Okay. if x is any real number, then we have x squared greater than or equal to 0. So no real number becomes negative when squared. Okay, so we formally introduce the imaginary unit, that is square root of -1. So what this means is not clear at this point, but just take it as it is and formally. Okay, so formally, if we define like this, then I squared is -1, which is of course negative, less than 1. And so this is called imaginary unit. Okay, and this definition is very formal and it doesn't mean anything at this point. But by this operation, how this behaves defines what this is. Okay, and this number I times any real number b. B is a real number. So this is called, such a number is called an imaginary number. Okay, and for any real numbers a and b, we formally write a number like this, a plus ib. What this addition means is not really clear, but we just treat this as a formal number, and this is called a complex number. Okay, and if this b, imaginary part, and this is real part, and imaginary part b is 0, then this happens to be a plus I 0 can be identified with the real number a. So in this sense, the set of real numbers is a subset of the set of complex numbers. We will study what complex numbers are in more detail in a later video, so wait for that. And at this point, we just finish at this point like this, and it's very formal and it doesn't mean really anything, but we will see what we can do with them. And that's it for this video. See you later.